Shor Code. So we have been following this book, and it is chapter 15 of this Kitaev and others book. So our main intention is to understand the one error correction code, which is the Shor Code. It's a 9-qubit algorithm code, which means that to save one qubit from environmental errors under certain conditions, we need 9 qubits. This is not the most efficient way to do it. The best one is with 5 qubits, but we will nevertheless do this. It involves less algebra, or maybe less notions. So yes, so as you may have realized, so what we are after is to save information that we have stored in a system from environmental errors. So we have a state psi, it's a qubit. It's some 0 and 1 and some alpha and beta. These 0 and 1 are orthogonal, these alpha and beta are complex numbers, they are normalized. And we don't know what that is. It is stored in it. We may or may not know. But we don't want to lose it. It has been kept in the system, and we want to keep it in a way that the environment is not able to destroy it. So typically what happens is that this thing tries to get entangled with the environment, and so if you write down the density matrix corresponding to this, it looks like this. And there are different types of decoherence mechanisms that acts on it. One of them, for example, is one which puts sort of an exponential with some lambda here. And the system deteriorates into effectively this very quickly. This lambda is positive. The t is the time. This is one of the things that we want to stop. There are other forms of decoherence that can happen. The main point is that we want to keep this thing as it is instead of getting this is. So this is a well-developed problem in classical machines, in classical computers. We store our files in the computers and they don't get destroyed. We will try to find the quantum version of it. Instead of thinking of it as a storage device, a storage mechanism, you can think of it as a channel mechanism as well. So instead of this being kept somewhere and the thing that is happening in time, you can think that it is going through some channel, and at the output you get something, and this is the state that you may get at the output, which you want to stop. You want to get this as the output. You want to keep the output the same. You want to find a mechanism that does that. Classical channels does that. You call your friend in Mumbai and whatever she or he is telling you, you get the same information coming. Roughly. So we begin with a simple classical case. By classical we mean that the system that we are handling can be written down in terms of a bit. It can be either a 0 or a 1. Typically, of course, you are much more than just a 0 or a 1, but all of them can be written down in terms of series of zeros and ones, several bits. So we will talk about a single bit. So, suppose we want to communicate or store a bit, a single bit. The communication channel or the environment of the storage device is noisy. Can sometimes flip the bit. You send a 0, it makes it into a 1. You send the 1, it makes it into a 0 with some probability. To protect the information, we make the following encoding. This is the thing that we want to store or send. We encode it in 3 zeros, let's say, and the 1 in 3 ones. Yes. This thing is called a logical bit. This thing is called a physical bit. The name implies that, this is the information that you want to encode or send, and this is the physical device in which you are actually encoding it. You can be different charges, different colors, or whatever. Has to be distinguishable. Moreover, we assume that there can be an error in only one of the physical bits. So we will try to protect our logical bit only against this type of an error. So the error is that either nothing happens, or with some probability, one of the physical bits is flipped. This is the only thing that can happen. This we are assuming. So we are assuming that we know the channel. We have sent many times and we have seen what is done in the channel, and then we are trying to do the encoding. So we are not doing a blind encoding. We know how the channel behaves, we know how the environment behaves, and by looking at it, we are trying to do an encoding that will be good enough for that channel. It may not be good enough for other channels. So now it's easy to see that this will work. The options at the receiver's end, or at the end of the time that you have stored, are, so you have your input, as if your input was 0, then the encoding was the 3 zeros, the 3 physical zeros, and then an error happens, and there are 4 options. There is this 1 0 0, 0 1 0, 0 0 1. Any one of the bits gets flipped, the physical bits, or nothing happens. We do the decoding by majority voting. We find out the max, which one is more. Which one is the majority? The majority is 0 in all of them. And this is the same as this. So this is the output. Simple. The same thing you can do for 1, yes? I'm not doing it. What we will show is that this simple thing works in the quantum case as well, with some interesting things.
Alpha 0 plus beta 1.
So by majority voting means we are measuring the 3 physical bits,
Exactly.
whichever comes out.
So this is a very good point. Actually, you see what, so that cannot be done in the quantum case, because measuring will destroy the qubit.
Also, there cannot be this copy 0 plus 0 0.
It also is a problem. So of course there are,
It will assume generate multiple of the same state.
no, this is not a good thing to do. Yeah, so if you can do that, then it's a good thing, but you will not assume that.
Let's say copy 0 to 0 0 0. That is possible.
Not 1 to 1 1. Alpha 0 plus beta 1 to alpha.
Yeah, 0 to 0 0 0 and 1 to 1 1 1, this will work. But psi to psi 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 will not work. Right? This is the no cloning theorem. I mean, psi to psi 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 does work for a given psi.
Right.
For arbitrary psi it will not work. Any two non-orthogonals will not work. not doing the 1, yes? You know the 1. So we'll go to the Shor code later. We will begin with something that is called a 3-qubit bit flip code. So this code will be able to protect a single qubit by encoding the qubit in 3 physical qubits in a certain way, under the constraint that there can be a bit flip error in at most one of the qubits. Bit flip error, in the classical case, bit flip is the only thing that can happen. In the quantum case, that is not true. There are many other errors. But here we will assume that there is, suppose we have a channel which only has bit flip, which changes the 0 state to the 1 state. But if I have 3 of them, it changes only one of them or none of them. If I have such a channel, we will have a method that will protect against such a channel. And only 3 qubit encoding is enough. We now have a qubit instead of a bit. With some A0 plus B1. 0 and 1 are orthogonal. Which we wish protect only from bit flip noise, and that also only in one of the, we will tell the restriction later. It will be only in at most one of 3. So first of all, the note is that, as we have been discussing, looking at the classical case, we may want to prepare this, but this is not allowed. Yes, this is the no-cloning theorem. For an arbitrary psi, you cannot. You can do it if psi is from a set of orthogonal states, but that is the classical case. So what people discovered is that, but this doesn't. So if we are able to encode this into this, then it will work. It will work in the sense that we are with a channel that has only bit flip noise, so it can only change a 0 into a 1 randomly at the most. So only one of the qubits can have that situation, not more than 1. It can be 0 or 1 of 3. In that case, if I encode this to this, then we'll be able to save the qubits. Let us see how. So, what does this say? What we are doing is that we are using the logical qubit equal to this equal to 1, which we have actually done in the classical case. Also in this quantum case. Given this, we can prepare this one for arbitrary A and B. Yes, you have to apply two C0 gates actually. So you take this state, take the auxiliary systems as 0 and 0, and you apply C0 gate on the physical qubits 1 and 2, this one and this one. So this is the 1, this is the 2, this is the 3, the names of the qubits. So we are applying on this and this, which means there is identity on this. You land in a and a 0, there is a ket notation that I am not writing. Yes? 0, 0 is taken to 0, 0, and 1, 0 is taken to 1, 1 by a C0. You further apply C0 to 1, 2, 3, let's say, and you land in
Any
2, 3 also works, 1, 3 also works.
Please label 1, 2, 3 in the seconds.
Pardon?
Please label 1, 2, 3 in the second.
In the second step, I have not changed the order. This is 1, this is 3. This is 1. So just for the notation, these are my physical qubits. This is one, this is another, this is another. And this whole thing is my logical qubit. The logical qubit changes depending on what type of channel we are trying to handle. We are trying to save our qubit against. Question? just as in the classical case, we again assume that there can be error only in at most one physical qubit. Moreover, the error is only bit free. This is a very restricted scenario. We'll change this later. So let us again write down this the way the encoding and the error happens. So we have this thing. This was our qubit that we want to encode. This was the input. We take the auxiliary system, and this process was the encoding process, and we land in this. This is our encoded qubit, the logical qubit. And we have I'm not writing the kits. So either there is no error, which means I get this, or error in first physical qubit, which is only bit flip. So I get A100 plus B011, or it is in the second. So I get A010 plus B101, or it is in third. You get A001 plus a B110. So, I mean, the feeling that the things are under our control is because you see that all these four, they are in orthogonal spaces. So, what I have to do is I have to make a measurement that distinguishes between this space, this space, this space. This is exactly this is the projector of this, so it's the ket bra of this. And so on. These are rank 2 projectors, and since they are orthogonal, I will be able to make the measurement and I will be able to find out what has happened. And look that these are identity operators in the space of 0, 0, 0 and 1, 1, 1. Yes? Look, just measuring in the whole basis, if you measure in the computational basis, if you measure 0, 0, 0, 1, 1, 1, 0, 1, 0 and so on, you will destroy the qubit. You will suppose this one clicks, you know the state is this, it cannot come from here, but in the process you have destroyed the coherence. We don't do that. We take advantage of the fact that there are higher rank projectors that are also allowed within quantum mechanics. We make measurements onto these. So you have to think of it may actually be difficult to do it in practice, but we have to think of a Stern-Gerlach apparatus which has 4 outcomes, and if this one clicks, it means we are measuring with respect to this projection operator, and so on. And now if this thing clicks, it means none of these have come, it can only come from here, but being an identity operator in that space, at the output you get exactly the same thing. Nothing happens to it. Is this clear? The state, because A and B are arbitrary. So if you change A and B, so look at only this thing. If you change A and B, then this behaves as a qubit. Yes? It's just a big 0 and a big 1. It behaves as a qubit. But actual realization we have taken 0, 0, 0, 1, 1, 1. But for mathematical purposes, this is a big 0 and a big 1. The actual realization helps in stopping the error to happen, or it doesn't stop, but it lets you get rid of the error once it happens. But now this is a qubit. So if I operate on it with this 0 being the big 0, plus the big 1, then nothing will happen. The measurement, you will apply it on both sides and you will give the output, it will give you the same thing. So after this measurement, it tells you where the error has happened, in which qubit it has happened, or it has not happened anywhere. So if it is like this, if this one clicks, it means there's no error what has happened. If this one clicks, it means that the third qubit has flipped. You know which one has flipped, and you haven't destroyed the coherence. So what do you get? Suppose this one has clicked. This thing has clicked in your Stern-Gerlach, this one has clicked. You know that the third qubit has clicked. What do? You apply sigma x on the third qubit. You get back this, which is equivalent to what we had. If you want back your original thing in a single qubit, you apply the inverse C0s and get back to A0 plus B1 0, 0. So this is the main essence of all these error correcting things. In this, there are different types of error corrections, but in the textbooks the ones that have landed in the textbooks are mostly of this type. There are other categories, this decoherence-free subsystem and so on, those are different. But there are these neural network type ones. But this ones, so this is an active error control. Yeah, even if the error happens, I know what is the type, what are the limitations on the error I know, and I try to encode, I try myself to be prepared. I know there is going to rain today, so I take an umbrella. So I know what is, I mean, if it is going to hail, it will not be useful. So I know what is the type of error that is going to happen. I don't know whether it will happen or not, but I know what is the type, what are the possibilities and what are the limits. This I know. So in that case, in this, even though there is this coherence and all, there is a no cloning theorem and these type of things, you can still correct the error. So this was sort of a big success in quantum information processing. And that is a priori, I mean, once you see it is of course very easy, but a priori it's because of the no cloning theorem and others, it was, well, at least for me it was very interesting.
This is what people call quantum error correction.
This is one error correcting code, yes. So we will make this whole thing systematic because this helps in running the whole show, because here you see we have made have only a bit flip thing. So there are more types of errors. There are other types of errors, and we'll make this, whatever I said here, we'll make it more systematic. This will help us in the more general scenario. Also, how do you make this measurement? These are 3-qubit measurements. These are sort of difficult ones. So actually, it's not so difficult, and we'll see how it is. So to make it more systematic, let's start and then. So there is, we do this detection of the error in a more systematic way. It's called error detection, or sometimes it's also called syndrome diagnosis. More fancy name. So what you do is you measure sigma z on the first qubit. So whenever I'm writing the name of the qubit is the physical qubit. Tensor sigma z2. So this means that I'm measuring, the operator is this. There is the identity operator in 3. This is the 2-qubit identity operator. This is the 2x2 matrix, 2x2 identity matrix. I'm doing nothing, so it means I'm putting the identity operator. Yes? You can write this as, well, let me do it for one case. In the next ones, you will understand how it is done. Yes, sigma z is this. This is in 1, this is in 2. I'm not writing the 1, 2 anymore. It's in order. The first one is 1, the second one is 2, and so on. And there are only 3 anyway. And this I keep in operator form. Yes. And now this is just writing it in another way. What we are doing sigma z measurement in the first physical bit and the second physical bit. But we'll come to that. So we have measured in the projectors these two. This is a projector and this is another projector. So if you now look at this and this options, you see that this does not destroy any of the inputs. Whatever is the input, it either never clicks or it keeps it as it is. It clicks and it keeps the output as it is. As it output the same as the input. It acts as an identity operator on the input. Or it is orthogonal, so it doesn't go through in both the options. Yes, whatever is the output, whichever clicks and whichever is the input, it doesn't change the measured state. So what it does is essentially, so the first one will click if it is in either one of these two. The second one will click if it is in one of these two. Yes, because look at the first, because you are doing on the first two, and look at the first two. Here it's 0, 0, 1, 1. This is 0, 0, 1, 1. So either if the thing that has come is these two, the first one will click, nothing will happen to it because of the identity on that space, or this one will click. If this one has come, if one of them have come, then this one will click, and again nothing will happen to it. Nothing will happen to the input. So the measurement compares the first two physical qubits in that whether they are in the 0011 sector or the sector. It finds out whether it's here and here or here and here. Next, we measure two, three. And this will go on with this thing coming here, or you can just write this as 2, 3, sorry, yeah, 2, 3, and this one as 1. We are writing on top, right? And so on. It will be the same thing with this thing is in now 2, 3, and 1. This thing is in 2, 3 in 1. You can write this I in front. It doesn't matter as long as you remember what is what. Again, this one holds. And instead of this first, will be the 2 and 3, the last two. Now you find out whether you are in these two or in these two. With these two measurements, you can find out which one of the four you are in. So this, I mean, this is equivalent to the measurement in that these four two-dimensional rank 2 projectors. But I want to write it in this way because it will help us in future. And once we have found out where the error has happened, you apply the sigma x, the bit flip, the sigma x operator, you get this thing, and you apply the inverse of the C naughts to go to the physical.
So measuring this sigma z cross sigma z on 2 and 3, or 1 or 2. I asked you once earlier, you said like we measure sigma z cross I and I cross sigma z successively. Do we do that?
So, in the case where you want to, you don't care what happens to the state, that you will do that. Not in this case.
Not for a higher order rank.
Yeah, because here you want to save because once you make a measurement, so here we have to do the measurement in such a way that these things come out. It should not be that we make a measurement in 0, 0, 0. This should not be done. So this should not be one of the projections that come out. So the point that has to be, we have to be careful here is that we have to do the rank 2 projection measurements and not the single rank projection. Once we are careful about that, then you can do it in whatever way you want, but it should not become rank 1 measurements, so that the coherence is, yeah.
So if it's a rank 2 measurement, something is being traced out, right? One of the bits.
No. It's not about tracing out. Rank 2 measurement is not about tracing out. It's about not looking at the difference between these two at the quantum level, meaning that you don't look in the sense that whatever coherence comes out in the superposition, that is preserved.
Physically, what we have measured.
You are measuring the error while keeping the, so the error can be measured in different ways.
In terms of.
So if you make a measurement in the 0, 0, 0, 1 and so on, you still find the error. But out of these different methods of finding the error, we do the one which preserves the coherence, because we want back the qubit that we had encoded. So this type of error correction is called, has been called active error correction, because you let the error happen and then you find what it has happened and you retrieve it, you remove it.
But this is not a measure in the sense we are taking a statistical measure. We are just seeing where the particle goes.
What do you mean a statistical measure? I mean, it's in the measure theoretic language, you are dividing the identity into different ways, So you are, so this is a finite dimensional case here. Measure is a trivial thing. It's an 8-dimensional space anyway. So you are dividing the 8 dimension. You can divide it in many ways. You divide it 2 by 2.
In the sense that when we say we are measuring a classical, an ensemble, like we want to do a tomography of it, we measure each component of the of the row matrix, density matrix. So there we destroy the state each time we measure.
Exactly. Because you want to do tomography, you want to know the state. Here we don't want to know the state. You want to keep the state.
This gives you A or B or not?
No, it doesn't give. This is the point.
Nothing, no information.
No information. And we have to be, because no cloning stops you from doing that. This is the point. That this we discussed some time back, that if you have a state psi, so if you have a state psi that is either psi 1 or psi 2, and if you put an auxiliary system, and if you want psi 1 and psi 2 back, then the only way to do it is to keep this thing the same. It can be changed to something else, but they will have no information. They can have only if they are orthogonal. If they are non-orthogonal, then you will have no information. I mean, you can change some phase, but nothing else.
So, if I am a 2-qubit system, I want to measure something like sigma z cross sigma z and get the density matrix value on it. How is that then? We break sigma z cross sigma z in 2 measurements of sigma z cross I and I cross sigma z.
If you want to do it in the tomographic sense, yes. And there you can do it separately, there it doesn't matter.
Separately in the sense that once we apply I cross z on one, like sigma z on one particle, and then after that sigma z on
Yeah, they commute, so it's after doesn't have a meaning.
then that has to be known, like which has been applied first by classically contacting each other.
No, because tensor products of operators, so if it is a tensor I and I tensor B always commute. So the order, the time doesn't come into the picture here. The order doesn't come.
Yes, but whose output result, when A and B measure this locally sigma z, what does he get when he measures sigma z? He gets some number and
He gets information about the output, about the input.
yeah, but he'll not know what the output corresponds to until
No,
they know.
why not know? He will get some information about the input.
What?
He will get some information about the
Yeah,
input
but
out of
he
it.
won't know what it is corresponding to unless they know in which order they perform the measurement.
No, why? The order doesn't come here. This is what I'm trying to say. The order doesn't come in the picture.
No.
When you will finally find the correlations, you will have to look at both the sets of data.
Yeah, so that's what I'm trying to understand.
No, but this is not relevant here. I mean, here you measure it this way. Any other question? Okay, so do it next. So next day we will generalize this to other types of noise.